about Genesis. I would like to talk about Genesis in my presentation and focus on one particular technique of Genesis, namely GNSS, and discuss the impact of certain systematic errors on Genesis-derived products. I guess after a couple of presentations, now I do not have to really introduce Genesis anymore. One satellite containing 4 space-geodetic techniques to be launched in 2028, and the aim is to improve the terrestrial reference frame by ingesting data of these space-geodetic techniques on that satellite. But of course, a lot of applications on the ground, that is in the interest of a lot of applications on the ground, even though after Athena's last slide, I'm not so sure anymore about that statement. But nevertheless, so the Genesis satellite, how it's going to look like, I'm not really entirely sure whether the design is already finally decided. There are designs around, like in this shape, in the white paper of 2023. More recently, there have been new designs shown. We were using for our simulation study this design here, but it's not really important for the purpose of this presentation here. What is sure, on the other hand, is that the satellite is going to fly relatively high at an altitude of about 6,000 kilometers. That's mainly driven by VLBI visibility constraints. And that means that the GNSS signals which are received by Genesis are transmitted at the GNSS transmit antennas at relatively large nadir angles, up to 28 or close to 30 degrees. That is much more than what we are used to on the ground or in LEO. And due to that unfavorable GNSS visibility conditions, there is actually going to be a zenith and a nadir pointing GNSS antenna mounted on the Genesis satellite. So it's an interesting satellite. It's going to be challenging. And Kur et al. Have recently demonstrated that ingesting Genesis data in a Galileo-like precise orbit determination and clock determination is really helpful, and Genesis can really benefit. So it's going to be interesting. And what I'm going to focus here in my presentation is a particular issue, namely that at such large nadir angles of close to 30 degrees, we only have little information about the characteristics of the GNSS transmit antennas, especially when it comes to the gain patterns, but also the phase or the code variations. That's not really well known for most of the GNSS transmit antennas. And also, the GNSS signal strength might be an issue because we have drops of the gain when we go to larger off-boresight angles. Now, Montenbroek et al. They have recently analyzed these issues, these visibility conditions for Genesis quite detailed, and they came up with a quite comprehensive link budget simulation environment to simulate realistic GNSS data for Genesis, really taking these link budgets into account. And having that, we pose the question, what is the impact of uncertainties in GNSS transmit antenna phase variations, PVs, at large nadir angles that are very likely to be there to the contribution of Genesis of global TRF. And we have to keep in mind that we would like to avoid the in-flight calibration of such PVs, because, as it is usually done for LEOs, because that would of course weaken the GNSS contribution of Genesis. Our method that we employ here is a closed-loop simulation. We start with some simulation truth, the constellation, GNSS constellation, ground station coordinates, the Genesis trajectory. We feed that into a simulator to generate GNSS data for ground stations and the Genesis satellite. We feed that into a parameter estimator to estimate some orbits and geodetic parameters, which we can then again compare to the simulation truth to assess the quality. The simulator is done in DLR, and the estimation is done here in Bern using the Bernese GNSS software. And I have to admit or say that there is some slight inconsistencies in terms of station coordinates modeling between the simulator and the parameter estimation, especially when it comes to tidal loading models. But as I will demonstrate in a minute, we can consider these inconsistencies as natural uncertainties that we have in the models. That map shows the selection of 100 IGS stations which we are using, where we are generating simulated ground station data for our simulation study, and that shows what kind of antennas or antenna patterns we are using, phase patterns. For the ground stations, we are using the regular IGS 20 ampex file. For the GNSS satellites, for GPS, we are using the LMB20 model, which has been introduced by Oliver this morning, extended to 30 degrees nadir angle, and for Galileo, we are doing a quadratic extrapolation of published patterns from 20 to 30 degree nadir. For the Genesis receiving antennas, we are using some Sentinel-6A patterns that have been derived. The simulation is done for 37 days in 2023, covering basically the entire range of beta angles that is possible for that orbit that we have selected. The GNSS products, the simulation truths, so to say, these are the code final orbits and clocks and ERPs and biases. Station coordinates are some IGS cumulative solution, and we use some ionosphere GIMS from Code and Nequip G for Genesis. The estimation is done based on a non-differenced GNSS data processing. We estimate a whole bunch of parameters, basically station coordinates. We're using no net translation and no net rotation constraints here. We're estimating the Earth rotation parameters, the geocenter coordinates, and then some site-specific troposphere parameters on top of the GNSS satellites and the clocks, and on top of the Genesis orbit. The data sampling is 3 minutes, which is about 80,000 parameters per day. Most of the parameters are the satellite clocks, the epoch-wise satellite clocks that we estimate here. Let me show you the zero test that we can achieve currently. Zero test in the sense that I just do a PPP based on the simulated data for the ground stations only by using the code final GNSS products and the correct transmit PVs. These are the differences with respect to the simulation truth. And you see in an ideal world we would be very close to zero here. We are not very close to zero. Well, 1 to 2 millimeters actually, and that's showing the inconsistency between the station coordinate handling or modeling between the simulator and the estimator. However, that's about the same order of magnitude as we have differences between the different IGS analysis centers, and that is showing us that we can interpret these differences actually as a realistic model uncertainty in our simulation. Still not sure why the east component here seems to be the largest. There is no rotation in there or something like that, but we still need to figure out what's going on. That's the zero test for the Genesis orbit. When using the simulated data and just computing the orbit of Genesis, just doing a POD, using the nadir antenna, we are able to reproduce the orbit on a level of 1 to 2 millimeter RMS in all components. When using the nadir antenna, when using the zenith antenna, things get a bit more tricky. The zenith antenna is much more challenging because the data is much more sparse, has much more gaps. Ambiguity fixing becomes more tricky, and we also have a couple of days where it's really bad and we need further inspection of these days which are really off. So please just ignore these days in the following slides. And when combining the nadir and zenith antenna for Genesis, then everything in average gets better, apart from these 2 days and maybe 3 days, which got worse. Yes. Now doing the full parameter estimation, and by full parameter estimation is now really estimating all the parameters that I was listing on the previous slide, using the correct PVs. This is what we get when starting in blue only with the ground stations, and then adding first the nadir, then the zenith, and then both antennas of Genesis. We see a general improvement of our GPS orbits in this case. This is differences of GPS orbits with respect to the simulation truth. We see some improvements, although these improvements are not as large as was previously shown or recently shown by Kur et al. They have demonstrated an improvement of Galileo orbits of up to 50%. Here we are more talking about a few percents of improvement, but Genesis helps here anyway. And I have to say that the code final orbits, these are 3-day orbits, whereas we are doing here a 1-day processing, so we have a slightly worse comparison, or it could be better if we would do here also a 3-day processing. But it doesn't matter for the relative comparison, of course. This is just showing the formal errors of the geocenter, of one of the geodetic parameters. again demonstrating that, as we have seen also in previous presentation, the formal errors of the geocenter is significantly improving when including Genesis data. Now let's add some phase pattern errors. And we have constructed these phase pattern errors by computing differences of antenna phase patterns with respect to some block-specific means. We have scaled them and to orders of magnitudes that we believe are realistic when going to large nadir angles. We believe that these errors are not unrealistic. We have made sure that at smaller nadir angles, so below 17 degrees or something like this, the errors are basically zero because we can trust from the ground calibrated antenna patterns here. And then we have added these PV errors to the estimation step. We did not repeat the simulation. For the simulation we used the correct ones. For the estimation we then used the erroneous ones. And let's see what's the impact now on the Genesis orbit. Just checking how does the Genesis orbit react when adding these erroneous PV maps. We can see that in terms of 3D RMS value we go from 3 to 4 millimeters. So we see a slight degradation of the orbit, of the Genesis orbit in a POD only solution. It's a degradation, it's not a huge degradation, but there is some degradation there. When doing the same comparison with the GPS orbits, so again doing the big estimation with all parameters, including the GPS orbits and Galileo orbits, the GNSS orbits, they go back to a level which was similar to when we had only ground stations but no Genesis included. That's the conclusion that we can take from that plot here. That when in blue is only the ground station, only using ground stations to compute the GPS orbits. In orange, including Genesis, nadir, and zenith antenna, and then in green when adding these errors. And we see that we have some degradation of the orbits again. Now, the last plot that I'm showing here is that the geocenter, this is an example of a geodetic parameter here, geocenter x, y, z coordinates. We can also say that including Genesis helps to stabilize, to go towards zero, because zero is the truth that we're using for the simulation. So adding Genesis from blue to orange helps to go to have a more stable geocenter estimation here, and then adding on top of the PV maps these errors, again, very slightly degrades these estimates. So it's a small degradation. It is a degradation, but well, if we are aiming for the 0.1 millimeter or 1 millimeter, we should take that actually into account. That brings me to the conclusion. Take-home messages here are that, first of all, the Genesis tracking and the GNSS tracking of Genesis is much less straightforward than it is for LEOs usually, especially for the zenith antenna. We still struggle quite a lot to process this data. It's not easy. It's quite tricky. We have established a simulation environment to study the impact of such systematic errors on the solutions. And what we think are realistic GNSS transmit phase pattern errors. They do have some visible impact on GNSS orbits and also on geocentric coordinates, for example. And what that means is that in order to really fully exploit Genesis for future TRF contributions, characterizations of the GNSS transmit antennas up to large nadir angles should really be known or made available to the extent possible. Thank you very much.